Okay. Now, what we have not talked about at all what we haven't talked about at all in M-ary is the matched filter. So what is the optimal filter? Well, if you think back to what I just showed you, I showed you that the probability of error is m minus 1 over m times c d over 2 sigma squared. And I also said a special case of this is binary, which is 1/2 c 1 minus alpha s 0 over 2 sigma squared. Is that right? Yeah. So it stands to reason that due to the similarity in these, that the optimal solution down here is the matched filter. And basically that solves the problem in binary. In M-ary, the m's appear out here. So they're not an argument under the RFC. So they actually disappear in the optimization. And you can show by going through the exact same derivation that I did in before the midterm, you can show that the match filter is still optimal over here. So it's the same match filter. Now we have a filter matched to the basis signal S. So remember back when we started talking about this, we said that our modulation functions S I of k is equal to some constant alpha I times the basis signal S of k. So it is possible, like I said, to go back to the derivation we had of the matched filter and go through it and show that the matched filter is still useful here. Basically, you'd be matching it now to S of k. But we're talking about signal space now, so it makes sense to talk about this in signal space terms and look at this geometrically. So here's an alternative way of looking at the optimal filter. So remember when I was proving the matched filter, so my matched filter impulse response is h of k. My noise-free filter outputs, therefore, are SI is equal to SI of k, involved with h of k, evaluated at NB, which is the sum from I equals 1 to NB, SI of k, h at, excuse me, SI, h at NB minus I. But let's let, remember I did this, I used this trick before. I rearranged my h's so that I didn't have this weird expression, this awkward expression. Let's let h hat of k is equal to h of NB minus k. And then this expression is equal to the sum I equals 1 to NB SI of I times h hat of I. Okay, what vectory kind of thing does this look like? Dot product, exactly. So this is now expressed in terms of the dot product between two vectors. let's let vector Si be S1, S2, and so on up to S and B. And let's let H hat vector be H hat 1, H hat 2, and so on up to H hat and B. And then, if that's true, then the IF noise-free filter output Si is just equal to H hat vector dot Si vector. So that's very convenient, because now we can start talking about linear algebra rather than convolution. So first off, remember the problem here, which is find H maximizing M minus 1 over M or C D over 2 root 2 sigma squared. So the problem is both D and sigma squared are functions of H. But because this can be expressed as a dot product, what I'm going to do is I'm going to normalize the variance. Or I'm going to normalize the filter, and that'll let me fix the variance and just work on D. So the variance, sigma squared, is equal to N0 over 2TS times the sum over from I equals 1 to B.
Sir,
yes?
I have a question. Can we get rid of M minus 1 over M here? Because we're just trying to maximize whatever instead of
Yes, absolutely. So this is a constant. This is not a function of H, M minus 1 over M, so it plays no part of the maximization. Sum from I equals 1 to B of H hat I squared. What vectory thing does this look like? Norm. So this is N0 over 2TS norm H hat vector squared. So what I'm going to do is I'm going to restrict myself to filters that are unit norm. We saw that in the binary case, the norm, you could multiply the filter by a constant and it made no difference. So what I'm going to do is I'm going to argue that the filter is normalized. That fixes the variance because nothing here depends on the signal. So that fixes the variance, and now I'm looking at D. So this is now equivalent. Excuse me. Find H minimizing. We want to minimize probability of error. So now the problem boils down to maximize D.